This short video shows how you can patch a sequencer very simply, while ultimately gaining some truly incredible features. The sequences created can have up to 128 steps, each delivering both a voltage and a gate signal. Unlike many other sequences, each step is defined not by a voltage but by a note that appears clearly. This makes input very convenient and eliminates the need for a quantizer. You can define a specific duration for each step or group of steps. This allows for rhythmically interesting sequences while avoiding tedious and complex clock programming. Finally, it is possible to associate a specific envelope shape with each step or group of steps via an ADSR module control via the patch. All these features are made possible through the use of two extraordinary modules from the VCV Rack free library. Let's take a step-by-step look at how this patch is created. We first load the Basically module from the VCV Rack free library. Its expandable window allows us to enter the few lines of instructions that appear on the screen. At the end of the video, I'll detail each of these commands, explaining how they work. If you'd like a general overview of this module, simply refer to a previous video in the channel. However, in the case of this patch, this isn't necessary. Basically's role is to control the step sequencing. Basically is also responsible for collecting the pitches of the notes in the sequence and creating gate signals with the durations we have programmed. We then load a reftone module from the BOG audio collection. Its pitch and octave buttons will be used to enter the pitches of the notes in each step. In this example, this is the note C3. The volt octave output of reftone is patched to Basically's IN1 input. This way, the pitch of each note in the sequence present on Basically's IN1 input will be read and then processed by its program, as we will see later. We now need a voltage module from NIST, which will be used to enter, in its lower part, the duration of each step expressed in seconds. In the example, the current step has a duration of 0.25 seconds, which corresponds to the value of an eighth note at a tempo of 120 BPM. The output of voltage is patched to Basically's IN2 input, and the voltage routed to this input will be processed by the Basically program. An 8-face module is now loaded into the patch. The 8 green LEDs aligned on the front panel each represent a slot, in other words, a memory location corresponding to a sequencing step. In each slot, you can store the pitch of the note in question as well as its duration. To create sequences with more than 8 steps, you can load a +8 expansion module from the Stormelder collection. By placing it immediately to the right of 8-face, the number of steps is increased to 16. In total, it is possible to increase the maximum number to 128 steps by successively adding expansion modules. It should also be noted that 8-face can store the settings of any module present in the patch. To do this, you must first associate the module in question with it, which is done using the Bind Module option in the context menu. In our case, we associate the reftone module and the voltage module with 8-face. Later, we can also, if desired, associate an envelope generator module with 8-face. This will allow us to customize and memorize the envelopes for each step. These envelopes can be automatically retrieved when the sequencing is executed. The progress of each step of 8-face is controlled by the Basically program. Also, Basically's OUT3 output is patched to 8-face's CV input. Whenever it is necessary to advance a sequence step, Basically will send a CV trigger. To complete the patch, we load the MK3 module, which will generate triggers. Its upper output is patched to the reset input of 8-face. The corresponding button will reset the sequencer. Its lower output is patched to the run input of Basically. The button will then be used to start the sequencing program. With the utility patch now complete, we move on to its implementation. The first step is to complete it with an audio chain of our choosing. For the demonstration, I limited myself to the bare minimum by loading the VCO, the ADSR module, the VCA, and an audio module, all from the VCV collection. The sequencer section is connected to the audio section by patching basically's out1 output to the VCO's volt per octave input. Basically's out2 output is patched to the ADSR module's gate input. In this example, we will be testing a 15-step sequence. A +8 extension is therefore required. It is loaded and placed immediately to the right of 8 face. Using the latter's context menu, we set the number of steps in the sequence to 15. The first 15 LEDs then turn dark green. It is imperative to associate reftone and voltage with 8 face. If the sequence is one in which all steps have the same envelope, it is not necessary to associate the ADSR module with 8 face. Otherwise, this association will also allow each slot memory to store the envelope shape of each step. Memorization of each step in the sequence can now begin. Hovering over each slot displays its status, empty or occupied. We want the first step of the sequence to be the note A, in the 4th octave, and for its duration to be 0.6 seconds. A left click on the first slot tells 8 face that this slot is being memorized. The reftone knobs are then adjusted so that A4 appears in the display. A value of 0.6 volts is then entered into voltage. To memorize these values in the slot, the switch at the bottom of 8 face is now toggled to the W position. This position corresponds to write mode. Now, a further left click on the first slot causes the LED to flash red. This red flash indicates that the module is ready to memorize, in the current slot, the current settings of all associated modules. In our case, reftone is the pitch to be memorized, and voltage its duration. By switching the switch back to the R position, the recording of the associated module values in the slot is confirmed. The red flashing then stops and the LEDs turns light green. An identical procedure is used to memorize the next step, which will be an E note in the 4th octave. We set its duration to 0.25 seconds. We then repeat this procedure for each step in the sequence. I'll spare you the visualization of this step. Before moving on to listening, I'd like to point out that left-clicking on an occupied slot returns the associated modules to the configuration they had when the slot in question was memorized. Before starting the program, it's necessary to set the style knob to the 2nd position. This corresponds to a looped program execution. To stop sequencing, it will then be necessary to switch the style knob to its 3rd position, which interrupts the basically loop. Let's listen to the result of the memorized notes. Please don't focus on the poor musical quality of this production, which is purely educational, but rather on the ease with which the note durations could be customized, which was the initial objective. We can now move on to the last part of the video, which explains each of the instructions of the sequencing program managed by Basically. In line 1, the voltage retrieved from input in 1 is sent to output out 1. In other words, the voltage corresponding to the note produced by reftone, whose output is patched to in 1, is sent to the VCO's volts per octave input, which is patched to out 1. In line 2, a voltage of 10 volts is sent to output out2, to which the envelope generator's gate input is patched, causing the gate to go high. In line 3, the voltage value present at in2 is retrieved. This is the voltage delivered by voltage and corresponds to the note's duration expressed in seconds. Since in basically, durations are measured in milliseconds, this value at in2 must be converted to milliseconds, which is done by multiplying it by 1000. The wait instruction then suspends program progress for the resulting duration. Since the gate is high, the VCA allows the note to pass through for this period. In line 4, a 0-volt voltage is now sent to out2, which resets the gate to its low state and, consequently, stops the note. Line 5 suspends program execution for 1 millisecond so that VCV Rack and basically remain synchronized. Its absence causes the program to crash. In line 6, a 10-volt voltage is sent to out3, to which the CV input of 8 phase is patched. After a millisecond of waiting, imposed on the program by line 7, a voltage of 0 volts is sent to out3. In summary, lines 6, 7, and 8 correspond to sending a trigger to the CV input of 8 phase, which causes the sequencing to advance one step. Line 9 suspends program execution for 25 milliseconds. It only serves to maintain synchronization between basically and VCV Rack. This value has been evaluated experimentally. A lower value would seem to not guarantee lasting system synchronization. Since the program was launched in loop mode, it loops back to line 1, but now executes the next step. We have reviewed all the program instructions. This concludes this video. I hope the patch presented will be useful to you and can be integrated into your future productions. Please feel free to email me for any clarifications that may be required. Thank you for agreeing to accompany me throughout this brief foray into the vast world of VCV Rack.